Okay, so what I want to do now is discuss the existence of a non-measurable, non-Lebesgue measurable set. So this is a bit funky and maybe specialized, so you might question whether this is the best use of time. But this is often asked in the prelim, particularly construct or discuss the existence of a non-Lebesgue measurable set. Write, in some sense, construct a non-Lebesgue measurable set. Technically, you're not constructing it, you're just showing it exists. Right, for that reason, it's worthwhile to go through, and I'm going to do everything the book does, just a lot more detail. So like the book, we need the following proposition. Let's suppose I have a measurable set E. Let's assume it's bounded in the usual, traditional sense. We all should know, what a set, bounded set means. Well, it just means that there exists positive M where absolute value of x is less than or equal to m for any x in E. That's all it means. Okay, so suppose there exists a bounded countably infinite set capital lambda where the following is true. This collection here are pairwise disjoint. Okay, so if there's any ambiguity, this set here, remember, is going to be the set of all lambda plus little e, where little e is in big E, right? Okay, so the claim is that if there exists this countably infinite capital lambda where this collection here is pairwise disjoint, then the measure of E has to be 0. What is the proof? Proof is pretty straightforward, actually. Both of these are bounded. So that means this union here, we're assuming this is a disjoint union. Well, this obviously is bounded. It's measurable because, this is countable, capital lambda. So that means the measure of this disjoint union here is finite. It's a bounded set. So the measure of E not being 0 gives us a contradiction to this. Because E is measurable, lambda plus E is measurable. This is countable, so I can use countable additivity. This is a disjoint union. So we haven't used the fact that it's infinite yet, but at least it's countable, so this is fine. We'll just use translation invariance. So this is countable additivity. Now let's use translation. Let's use translation invariance. Lambda, little lambda, and big lambda, m of e. Well, if this is not 0, then we're adding up the measure of e countably infinite number of times. So if this is true, then this is infinity. Well, it's not infinity. This is a bounded set, so the measure is finite. So what's going on here? What's going on is this is impossible. It's impossible that this measure here is not 0. Okay. All right, so okay, so now we're going to do what's often called, it's called in the book, it's the Vitali construction. It's due to, I forget his first name, but a early 20th century mathematician named Vitali. Right. So let's say E is any subset of R whatsoever. I want to define an equivalence relation on E as follows. It's a pretty mundane equivalence relation. The book calls this rationally equivalent, this equivalence relation. So for X and Y and E, we say X is equivalent, and I'll use this kind of wavy equality here. We say that X is equivalent to Y if X minus Y is a rational number. It makes sense. It's sort of like, it's saying X and Y are the same modulo rational numbers. X is Y plus a rational number. Okay, so what I'm going to do, now you might not even object to this whatsoever, but in theory, I have to use the axiom of choice to do this. That's just, you really can't argue that. You have to use the axiom of choice to really do this. And it's funny because in the early 20th century, Henry Lebesgue himself, the person, the French guy who came up with all of this, he was doing kind of things similar to what I'm going to do. And he kind of at first was like, oh, this axiom of choice, this is silly, this is ridiculous, we don't need this mumbo jumbo. And then he realized, oh, wait a minute, I kind of implicitly am using the axiom of choice. I'm going to stop arguing all this, set theory stuff. So what do I do? I choose one element from each distinct equivalence class X, where X varies in E. Okay, so two possibly different X's might give me the same equivalence class. So what I'm saying is you just take the collection of all distinct equivalence classes and choose one element from each of these distinct equivalence classes. Maybe I should just put this here. Sorry, I always forget how to spell equivalence. So what I'm going to do is I'm going to place all of these into a set called script CE. It's kind of like a choice set. Now, so there's no theorem that says I can do this. There's no proposition, lemma, whatever. This is just an axiom that I'm allowed to do this. So by the axiom of choice, I'm allowed to do this. Okay. So again, you might be like, well, I don't object to this. You know, most analysts doing, you know, like PDEs, harmonic analysis, Fourier series, Fourier transforms, and whatnot. They really don't really think much about this, but anyway. All right, so let me write some very important properties. So one, if x and y is in CE, and x is not equal to y, then x minus y cannot be rational. And the reason is, well, every x and y in CE is a representative for a distinct equivalence class. So if x is not equal to y, and I should maybe make clear that E is a subset of the real numbers, so this here is a subset of the real numbers. Right, so C only consists of distinct of elements whose equivalence classes are distinct. So x cannot be equivalent to y. So x minus y can't be rational. Okay, just by definition. Two, again, really by definition of script CE, for each x and e, I claim there exists C in X, the class generated by X, rather, or there exists C equivalent to X, where C is in script E. Okay. Well, so this is really just by definition. If X is an E, then the class generated by X is an equivalence class. And we're saying pick some element from that equivalence class, throw it in CE. Let's say C is that element. So that means C is equivalent to X. They generate the same equivalence class. So C is in the class generated by X, and C is in script E. So what does this really tell us? So this says for any, or maybe for each x in E, there exists C in script CE, with x rationally equivalent to C. So that means x minus C is rational. So that means x minus C is a rational number. So x equals C plus lambda for some lambda in Q. Okay? And that's really what I need. For each x in E, there exists C where X equals C lambda, I'll do it like lambda, not that it matters, but lambda plus C. X equals lambda plus C for some rational lambda. All right, so some consequences of this I'm going to do on this page here. So by one, if I have capital lambda is a subset of the rationals, then I claim that these are pairwise disjoint. All these translations of script CE. So first of all, I should maybe have made this clear. I'm going to prove in a moment that script CE is not Lebesgue measurable. So why do I keep saying I really didn't construct this? Because you really can't constructively just choose one element from each distinct equivalence class. You only know that you can theoretically do that by the axiom of choice. You can't like literally write down an explicit formula for script CE. Right. Okay. And I'm going to do this, sorry, for E, for any set E with outer measure positive. And that's going to give me a non-measurable set. Okay, so, right, sorry, a little detour there. So this here is pairwise disjoint. Why is this true? Well, let's just see. Let's say X is in lambda 1 plus script CE intersection lambda 2 plus script CE. With lambda 1 not equal to lambda 2. So what does this mean? This means I can write X as lambda 1 plus C1, and I can write it as lambda 2 plus C2 for C2, well, for lambda, particularly lambda 1, lambda 2 rational. And for C1 and script CE, and C2 and script CE. So what does this tell us? Well, in some sense, I don't even care that these are equal to X. This says, in particular, that 0 equals, we'll just subtract off lambda 1 minus lambda 2 plus C1 minus C2. Okay, but this says that lambda 1, so we assume that lambda 1 is not equal to lambda 2. Well, that says C1 is not equal to C2, while C1 minus C2 equals lambda 2 minus lambda 1. Well, you subtract two rational numbers, you get a rational number, and that's impossible. What does one say? X and Y are in script CE, with x not equal to y, then x minus y is, sorry, I meant this is not rational. This is not rational. Okay. So x minus y is not rational. So that violates property 1. So that means there is no x in this intersection. So this is empty. Okay, so let's state the following theorem, which is often called Vitali's theorem, though you have to be very careful with what you call Vitali's theorem because there's a lot of theorems associated to the name Vitali. So the theorem is as follows, and this says that there's actually quite a bit of non-measurable sets. So if the outer measure of E is positive, then there exists A in E where A is not Lebesgue measurable. Okay, so how do we prove this? So, well, first of all, it's homework that I think I'm going to assign probably today, that there exists bounded E tilde, let's call it, with 0, or sorry, with non-zero and finite Lebesgue outer measure, or outer measure. Shouldn't really say Lebesgue outer measure. So there exists a bounded E tilde, that's a subset of E, that has positive measure, but also finite measure. Well, I guess I'm being a little redundant here because if E tilde is bounded, then the outer measure is certainly finite. So there exists a bounded E tilde with positive Lebesgue measure, positive outer measure, sorry. We don't even, you know, E is not necessarily Lebesgue measurable. Yeah, and this is an easy homework. So just, yeah, so I can just assume that E is bounded. In particular, I can just, all I need to do is find, to finish this theorem, I just need, or to prove this theorem, I just need to find a subset of E tilde that is not Lebesgue measurable. Okay, so I claim that if E is bounded, that script CE is not Lebesgue measurable. It is not in script M. Well, let's assume to get a contradiction that it is. All right. So I'm going to differ a little bit from the book's proof here, slightly. The book is kind of needlessly complicated here. So let's just pick anything. It doesn't matter what at all. Pick anything countable but bounded. Particularly countably infinite. So for example, lambda 0, capital lambda 0 could be all rational numbers between 0 and 1. That's an example that would work. All rational numbers between 0 and 1. Okay, right. So, right, so what did we proved just a moment ago that because we're dealing with a subset of, since lambda 0 is a subset of the rational numbers, we have that this set here is pairwise disjoint. That's what we just proved a moment ago. So this is pairwise disjoint, and we assume script CE is measurable. Then the little proposition we proved at the beginning tells us, this is exactly what the proposition we proved at the beginning tells us, that this has to have 0 measure. Sorry, script C has 0 measure. Script CE has 0 measure. Right, and again, that's just the proposition we proved at the very beginning on our discussion of non-measurable sets. Okay. Right. So I claim that E is a subset of this union here. That's not hard, but it's not trivial. Well, if X is an E, remember that as a consequence of property 2, we said that there exists we said, and we proved carefully that there exists C in script CE, and a rational lambda, where X equals lambda plus C. Okay. Well, C is in script CE. So this is obviously in lambda plus the set, lambda plus script CE. It's obviously a subset of this union here. So that basically takes care of the proof. So there's not a whole lot to this here. Well, what does this tell us? This tells us that, so just by countable subadditivity, the Lebesgue measure of E is less than or equal to I should say not Lebesgue measure, Lebesgue outer measure. We don't know whether E is measurable or not. It doesn't matter. So this is less than or equal to this sum here. Okay, well, use translation invariance. Well, that equals 0 because that proposition, remember, told us that we must have the measure of script CE to be 0. Okay. Right. And so the key thing is, remember that for this proposition that we start off with to be true, we needed script CE to be measurable. Because remember, in that proof, we absolutely did use countable additivity. We used countable additivity to get what's in the blue here, and countable additivity needs the fact that script CE is measurable. Okay, so the point here is that script CE rather, measurable implies that the measure of script CE is 0, implies, so maybe just make this clear here. So this here measurable implies that the measure of script CE equals 0 by the proposition we proved. By what we just did here, that implies that the outer measure of E is 0. Well, basically, what this is saying is the outer measure of any subset of the real line has to have 0. Sorry, the outer measure, this is basically saying the outer measure of any subset of the real line is 0. That's absolutely absurd. Okay? I mean, maybe more germane is that we assume the outer measure of E is positive. Okay? This is a contradiction. Right? So in particular, this is saying actually that every bounded subset of the real line has to have 0 outer measure. That's absurd. So this can't be true. Everything else we've done is fine. You know, this proposition was carefully proved. We proved countable subadditivity that implies that the measure of E, outer measure of E is 0. So this is what can't be true. So that means that script CE is not Lebesgue measurable. So it's kind of it's not hard, but it's a funky proof. So maybe take some time to digest it. Right. So as a simple corollary, this is kind of nice. So I claim that there has to exist 2 disjoint subsets of the real line where the Lebesgue measure, or the Lebesgue, the outer measure, because A and B are not we're not assuming that they're measurable. So this is not equal to the measure of A, outer measure of A plus the outer measure of B. So in particular, these two cannot be Lebesgue measurable. Okay. Yeah, the proof is assume not. Assume by contradiction that this is always true. So that means that for any 2 disjoint subsets of the real line, we always have this. right, so what does this tell me? For any A and E that are subsets of the real line, we have the outer measure of A, as always, is the outer measure of A intersect E, disjoint union A intersect E complement. And since we're assuming that outer measure is additive, no matter what two disjoint sets we have, this would be A intersect E plus outer measure of A intersect E complement. And this is true for any, in particular, fixing E. This is true for any A. Well, this implies, because E can be anything, A could be anything, this means that every single subset of the real line is Lebesgue measurable, and that's false. We just showed that that is false. So the conclusion has to be that there exists A and B disjoint subsets of the real line where the outer measure of A disjoint union B is not equal to the outer measure of A plus the outer measure of B.